two-dimensional Ising model and random matrix product.
Okay, thanks for staying. So this is work in collaboration with my colleague Francis Comets and Raphael. Is there? Yes. No? Yeah, he's there. Yes. Okay. So what am I going to talk about? I'm going to talk about the two-dimensional Ising model with bond disorder, and I will tell about conjectures and possibly some progress. Let me see in a second. So, this is not the first talk on this two-dimensional Ising model. So, of course, there is still a long story. Started off with Lenz, who proposed it. Ising, who solved the one-dimensional case, then made a mistake in higher dimension. Then Pye's argument, the duality after that, and then finally, without magnetic field and on square lattice and ferromagnetic interactions, there is the highly celebrated Onsager solution that gave birth to a field of research on its own. But let's say, say, while lots of different people were doing different things on the directions of Onsager's result, a certain amount of people were asking themselves of the stability of this result under introduction of impurities. In modern language, we would say disorder. So, because real systems are not perfect lattices, you could kill some bonds here and there with the density, but very small, maybe. And is the result of Onsager still valid? Does it still make sense? Actually, because that was really put into question in the 50s. Is the Ising Onsager transition still alive if you put inside a little bit of disorder? Actually, by the end of the 60s, I guess, thanks to, above all, to the works of Griffith, the common feelings that evolved, disorder, actually, if disorder smoothens a lot, disorder can even create singularities. In any case, the question has shifted to if impurities do not kill the transitions, how do they affect the critical behavior? So, okay, here is the two-dimensional Ising model. You have already seen it. With respect to the talks you saw on the Ising model up to now, I'm going just to look at something much simpler. I'm just think of the free energy. So this is the partition function, exponential of beta h. I sum over all the configuration sigma plus minus 1 indexed by the square of size n, and the Hamiltonian is this one. I just take nearest neighbors interactions. I'll give you something more explicit here, what I'm interested in, and the free energy is just the Laplace asymptotic. I would say, in any case, the exponential growth, the rate of exponential growth of the partition function, free energy density, I should say rather. Okay, but I will call it free energy through the talk. So actually, the model that you should keep in mind, the figure is this one, is actually Onsager. Onsager didn't solve only the case of really homogeneous Ising model. He solved the case in which on the horizontal line you put a certain energy, positive, E1, and on vertical one, a different one, E2. And actually, the result of Onsager is that the free energy is real analytic for every beta, except at one point, beta critical, which is given by this rather explicit expression. Actually, of course, the role of E1 of E2 is symmetric. Here it doesn't look like symmetric. Is equivalent to the standard one. I mean, you just play. And I prefer this because it's related to what I'm going to say next. And then at that point, it proves that the second derivative of the free energy diverges, and it diverges logarithmically. Another ingredient that we need of all this is the behavior of the correlations. But actually, it's not the correlation that you heard in previous talks. People were interested in the correlations at criticality. I just need the weaker result of the correlations out of criticality, approaching criticality. So correlations are exponentially decorrelating, so the truncated correlation, I should say, okay? And with a certain characteristic length, which depends on beta, this characteristic length, correlation length, diverges when you approach a critical point. And the divergence is like a power, and the exponent is nu. And actually, the exponent is just 1 for this model in 2 dimensions. Okay, that's all I need from so no sophisticated results at criticality and so on. Because what I'm interested in is introducing impurities. And just this slide is an overview of possible ways of introducing impurities. It doesn't contain the one that interests me, but just to give, actually the most natural one is to take E1 equal to E2, equal to E, and then take a small delta. Delta is just a positive number, small possibly, and put some impurities in terms of eta ij that are, for example, AD random variables that are centered with compass support to make things simple. So it's just the energies are all the same, except that they are a little bit perturbed by something random. And since E is positive and delta is small, the model is still ferromagnetic. If so, and so you can still define the free energy like before. You take the expectation here because otherwise it would be a random variable. But in any case, you could even not average with respect to the disorder because this limit is self-averaging. Doesn't matter. I mean, you get to a free energy like before. Depends on beta. It depends also on the size of the disorder, delta. It depends also on the law of the disorder. We forget about that. We just keep the dependence on beta and delta. And so actually, several people attack the problem, but they say somebody who did something that stayed, that was very successful as approach is the one of Bruce Harris in '74. And Harris came up with an argument based on the renormalization group. And the idea is, in a certain sense, very simple. I mean, you apply a renormalization group to your system at criticality or near criticality, and you want to understand whether the renormalization group tends to kill the disorder or tends to make it bigger. And actually, the analysis of Harris is kind of just a linear analysis of this. So on. I mean, if you at the linear level you figure out that the disorder kind of makes the disorder is killed by iterating the renormalization group, you say that the disorder is irrelevant, and you expect on large scale a behavior like if there was no disorder. In the other case, the disorder becomes bigger, and maybe you expect something else, but you don't know what to expect in that case. And actually, the argument of Harris is can be reduced to a back of the envelope computation, and it just says that if nu, the exponent, the correlation exponent, I mean, that you saw in the previous slide, times the dimension of the system is larger than 2, then the disorder is irrelevant, and if it is smaller, disorder is relevant. Now, I mean, he developed the thing for the 2-dimensional Ising model, the only system, the only model that he really could solve. Nu is equal to 1, d equal to 2, and he ended up precisely on the point that now is called marginal. At the linear level, you can decide whether the disorder will modify or not your critical behavior. And then, of course, people started, and 15, 20 years after, sort of the physical discussion relaxed to something that is now widely believed, is that in spite of being marginal, in spite of being not resolved by the Harris criterion, the disorder is supposed to be irrelevant, and in fact, but in a subtle way. So one expects that the free energy is still real analytic. For delta small, you have a little bit of disorder. Pay attention, the critical point changes. It's no longer the original beta critical, depends on the disorder. What is expected is that, but the exponent of the singularity, so there is still the second derivative of the free energy that diverges, but there is a little bit of smoothing effect. I mean, the logarithmic divergence has become a log-log. This is Vlad and Dotsenko. The conjecture is 92, or physical prediction. I want briefly to mention also that I never talk about external magnetic field. But in 2 dimension is well known, I mean also mathematically proven that the transition is the first order transition in the external field is killed by disorder, though from the point of view of the problem that I'm putting down, I actually have no idea what happens of the regularity in beta with external magnetic field. I think it's a completely open problem. But if you don't understand, the last remark is not important. So I won't be talking about this type of disorder, but I mean, this is maybe most. Here is the disorder I'm going to talk about. Actually, the point is that in this domain, there is a remarkable, exactly solvable model. The solution appears in a series of papers in the book of McCoy and Wu, but is already present in '69 in the first paper. And here is the disorder. You see it in the figure here. In the horizontal direction, it's just one constant. In the vertical direction, is random. So the disorder is in the vertical direction, and then it's just replicated. So it's just a columnar disorder. The disorder is one-dimensional, and we take E2 of j to be equal to a positive constant, E2, plus delta small eta j, and eta j is a RIID. Say compact is supported for now, it's not entering into technicalities. You define the free energy in the same way, and then you could try to apply Harris criterion. I mean, you just redo the back of the envelope computation. You would say, at first you say, but it's still like before, because 2-dimensional, by the way, I didn't insist enough, the nu is the nu of the pure system without disorder, is the one that you know how to compute. But actually, when you rethink to the Harris criterion, it's not the dimension of the system that you should take the dimension of the disorder. And here the dimension of disorder is 1. So actually, you get 1 times 1 smaller than 2, disorder is relevant. And actually, in fact, I mean, McCoy and Wu provide an explicit formula for beta critical of delta, you see it in a second, and they predict a major change in the critical behavior from a divergence of the second derivative to C infinity. So they predict only 1 point of phase transition, so analytic outside of S is beta critical of delta, and C infinity behavior there, and you will see in a second even more than that. This result has an enormous importance in itself, of course. I mean, you're able, in principle, you're able to solve. Actually, when I started off in statistical mechanics, I was hearing all the time there was this magical, exactly solvable. It took up to now to understand. Yeah, I don't know what is the common belief about the McCoy-Wu, whether it is really an exactly solvable model or not. What I'm going to claim with this talk is that it is not. But even if it's a remarkable result or prediction. In any case, the result is of enormous importance in itself, of course, but also for the major implications that it has for plenty of other models with one-dimensional type disorder, and say all sorts of d equal 1 disorder models. You see it in a second. So, and this is precisely this intermezzo here. What do I mean with all sorts of one-dimensional type of disorder? Here the key person is Dan Fisher, who worked a lot on quantum chains. For example, the quantum Ising with random transverse field. And in a series of papers, he really improved this renormation group for this system, and actually comes up with an explicit fixed point, which I call infinite disorder fixed point. In the literature is sometimes called strong disorder fixed point. In any case, what is interesting for me is that it may be natural for the people who are working in quantum systems, because there is a one-dimensional quantum chains mapped to two-dimensional classical systems, and so there is a map between this system and but precisely the McCoy-Wu system, except that it's very difficult to translate to the results between one and the other one. This map is in the limits is singular. So, but in any case, Dan Fisher uses a lot the rationale, at least there is behind the McCoy Wu analysis. And actually, and then lots of other people here put down some names. Apply the Den-Fisher approach to plenty of other models, finding typically, by the way, again, when there is a free energy in the game, they find infinite order transitions, this transition of type C infinity. This very strong type of smooth thing that doesn't kill completely a phase transition, but almost. Actually, I've been talking up to here like if all these results were kind of easy, well understood, maybe at the physical level. At the level of rigorous results, the results are really poor. I would say with a notable exception, the one-dimensional random walking random environment, that is an exactly solvable model, and then the Den-Fisher approach, applied by, I don't remember all the authors did, so prefer not to cite, but in any case you can derive plenty of results that are correct and that have been in part already proven before and then the rest completed by after physical works. But in any case, one-dimensional random walking random environment is almost exactly solvable. And I would also say that it gives you an idea of what is this infinite disorder fixed point, because in reality, if you have played with a one-dimensional random walking random environment like the Sinai walk, the walk is in reality a spectator of what is happening in the environment. With the environment, you build up a potential, and then the walk has not much, it like just chooses the time scale, but is really bound to the environment. I won't say more, I don't have the time. Outside of this case, I actually know only of two very recent progress, and they are both on localization transitions in pinning models. And here, we can say for which a critical point is kind of explicit, and so let me say, these pinning models are models in which, depending on the parameter, you find irrelevant and relevant regimes of the disorder. The irrelevant case is completely understood. There are plenty of works there, I don't have time to cite them. Also, in a certain sense, the relevant regime is sort of understood in the sense that we have smooth inequalities that says that disorder is relevant. But the problem is that when disorder is relevant, we don't know what is really the new singularity. And there are actually only these two results, very recent. The first one that I'm going to cite is very exciting, is not rigorous, but is the Diderot in 2014. And that looked at about these pinning models that I didn't explain carefully, but I don't have time. But I just want to say that the free energy that you see there for pinning models, so here, if I put F beta critical plus X, and here is X, like there, the free energy is trivial in the so-called delocalized phase, and then it becomes trivial, is zero, and then it becomes positive. And you see, when you know of such a behavior, you already know that the critical point is there. There is a critical point at least there. It cannot be analytic there. And also, if you want to study if you want to understand the behavior here, it's just a matter of doing upper and lower bound on the free energy on the right for X positive. So the Diderot for a simplified hierarchical version of this model actually applied a renormalization group transformation that actually magically in the limit yields the two-dimensional Costelli-Taules system. Two-dimensional, I mean the limit of the limit describing the fixed point of the Costelli-Taules transition, which is a two-dimensional ODE system. You solve it, and then you find this Costelli-Taules singularity. So you see, it is saying that the transition here becomes extremely smooth, exponential of -1 over square root of x. And actually, this result is probably now, I mean, I see why that they're saying that they have it, but it didn't come out. Just recently came out another paper for an even more simplified model. But okay, probably this result is rigorous now, even if I don't have the thing. there is another case that we have been able to solve with Quentin Berger and Hubert Lacroix. For people who knows spinning mechanism, which is called the copolymer. In a very particular case, we know the critical point, and in that case we have been able, shape of the free energy is the same, and then we have been able to prove a behavior like that. This time, the exponent here is not 1/2, it's 1 or larger in the class of models that we have studied. So I don't know. In any case, there are just 2 points that we are able to solve in this sea of models, and I'm just talking about pinning models. Then, of course, there are all the other models in which one is supposed to be able to apply these ideas. Okay, now I stop talking of, and I want to, I try to be a little bit more precise. We go back to the McCoy and Wu model, so this two-dimensional Ising model with columnar disorder, and here is the precise McCoy and Wu claim. The claim should be that for delta, so the size of the disorder, sufficiently small, and for a very specific choice of the disorder, they choose a very specific one, and then they lead the computation by making explicit integrals. This is like sort of confusing and difficult to follow in their arguments. They say that the free energy in beta is real analytic, except at the critical point that is determined by this equation that is totally explicit. E1 and E2 are constants. Here is the expectation with respect to this random variable, as easy as that. And moreover, at this critical point, the free energy as announced is C infinity, and this Taylor coefficients as this super exponentially growing behavior. So they have this, they characterize very precisely the singularity. So our contribution is simply, in a certain sense, I should simply say that after lots of time, and coming from another side, I think I understand what they did in all details. So I wrote here, unravel the proof in a somewhat more general context, and we made rigorous all the steps except a substantial one. So I don't have any proof of this one, but I mean, I put the finger, and I actually, in principle, as a mathematician, I should wonder whether this is correct or not. I see no reason for it to be true, but maybe you will have an opinion in a second. So yeah, first I give you the McCoy and Wu procedure without formulas, and then I will give it a formula trying to fill in all the gaps, except the one I cannot. McCoy and Wu start by taking precisely the Onsager root. So if you know, Onsager just does transfer matrix. A priori is a very bad idea in 2 dimensions because you're not iterating a small matrix, you're iterating a matrix which is size n, size of the system. But so you're iterating an operator, so our solving is not evident. But then there is an algebraic miracle that you can respect these things in terms of 2 by 2 matrices. And the point is that what McCoy and Wu observe is that with the disorder that I gave you before, the columnar one, if you go along the column, this is still true. And let's see what it gives. So once you have done these algebraic steps, this algebraic reduction, which of course is the basis of the solvability of the 2-dimensional Ising model, now if you're just considering the Onsager free energy, the problem is reduced to computing an expression that depends on the Perron-Frobenius eigenvalue of a 2 by 2 explicit random matrix that you will see in a second. Now, when you, and this just gets to a difficult calculus exercise to finish, you know, it would be a challenge to do it in less than 1 hour if you've never seen it before, to show that the free energy is C2 with a logarithmic divergence, but there's no secret at that point. But the point is that in the McCoy and Wu model, this step is perfectly fine, except that the Perron-Frobenius matrix now, and the Perron-Frobenius eigenvalue, is replaced by the leading Lyapunov exponent of a 2 by 2 matrix, of a 2 by 2 random matrix. So, and now and then it's less evident to do the computation. Much less evident. So now the McCoy and Wu procedure with formulas. So up to subtraction of an explicit analytic function, the free energy can be written as integral over pi, theta here, from 0 to pi, sorry, of this thing here, which is this L beta delta theta is the Lyapunov exponent of a product of IID random matrices that are just 2 by 2. And let's see, I mean, the structure is very easy. The theta dependence is only in A and B. They will appear here. Huh? And the random variable is lambda and doesn't depend on theta. Okay, now they will appear, they're slightly complicated, but they're not particularly complicated. I just respect completely the notation of McCoy and Wu. I could have simplified a little bit, but I prefer not. Let's see, okay. So A of theta and B of theta are here. Now the point, first let's start from here. Z1 and Z2 are just hyperbolic tangent of beta I1 and beta I2, except that I2 is random, and in fact lambda is just Z2 squared. So lambda is just a number between 0 and 1 random. In fact, almost a constant with a little disorder, the lambda that is there. Now, for the rest you see that depends on beta via Z1, but above all it depends on theta, and maybe the most important thing is that A, which is off diagonal, is 0 when theta is equal to 0 and pi. So at the extreme of the integral of integration. But otherwise, you see, this is a matrix with positive entries. The problem is only at 0 and pi, if you see as a problem being diagonal. Because when theta is equal to 0 and pi, sine of theta is equal to 0, A is equal to 0, and therefore the matrix becomes diagonal. So it should be even easier in a sense. Not completely true, okay. So now to understand even better, why don't we solve the Onsager case? So let's take E2 equal to a constant, and then we should be able to solve it, at least to understand what is going on. So delta equal to 0, so E2 is a constant, and now lambda is just a constant. Now if theta is different from 0 and pi, it's evident that this quantity here in beta, so it's just a Perron-Frobenius eigenvalue. It's just, you just obtain it by iterating, by understanding how big becomes the product of matrices when you iterate. So it's the leading eigenvalue of this product, of this matrix, sorry. And if you've ever played with that, you know that I haven't insisted on the fact that A and B have dependence that is analytical in beta. So you have a classical problem, you have a matrix with analytic entries, you want to know whether the eigenvalues are analytic. And they are, except when there are collisions. And, but the Perron-Frobenius doesn't collide with any other one. So as long as you stay far from 0 and pi, no problem. We have analyticity. Actually, let's look at the case. There is no problem here, even in pi. You will see next page, in the more complicated case. I prefer to look, the problem is when theta is equal to 0. When theta is equal to 0, when you compute the thing, you see that you get to a diagonal matrix, and you have these things that appears here. And this is equal to 1, precisely for the Ising critical point. So you see, this is precisely the collision of eigenvalues, 1, 1 on the diagonal. That happens only at the border of integration. In 0 here, in pi it doesn't happen. I mean, just that this quantity is always smaller than 1 in pi. You see it in the next slide. But now, but then non-analyticity, about analyticity, is non-analyticity, sorry, I apologize. So only when this quantity is equal to 1, then there is condition of eigenvalues, and okay. But okay, this is not a proof, this is just an argument, but once you know that, you understand that the problem from this integral comes from very small values of theta, and then you can start doing analysis around there and you solve it. Now, you step to delta positive, and then it's a mess in principle, because you can no longer solve the thing. And if you have just finished to do the exercise and you have spent at least 1 hour to figure out that the second derivative of is singular, there's a logarithmic singularity, I don't find it as a completely straightforward calculus exercise, but so at the moment you say, I mean, if I don't have this quantity explicit, what can I do? And in fact, I mean, the regularity in beta of this is a much more delicate issue. Okay, but in this domain there is an extremely powerful result, David Ruel in 79, that says that the application of beta associate this Lyapunov exponent is a particular case, of course this result is more general, is real analytic if we can find a cone that is contracted. So that if uniformly in your ensemble here of disordered matrices, so you apply to the green cone your matrix M for all the possible disorders, uniform in the randomness, and if this is mapped into a strictly smaller cone, so if there is a cone contraction, then you have analyticity. And, but then, in a certain sense, the Perron-Frobenius part is trivial, given Ruel's result. Because this is saying that, because if we know that the matrix has positive entries and bounded away from zero, then you know that if you apply it to the first quadrant, then it will contract the first quadrant. So for theta different from 0 and pi, you can take as C1 the cone to be contracted, the first quadrant, and an easy exercise. So like before, the troubles is near theta and pi in principle. So as I promised, now let's look at least at the intuitive level. Actually, the first one is not intuitive. This is again rigorous. Let's look around theta equal to pi. If you are exactly at theta equal to pi, the matrix becomes diagonal. And the other point is that this term that is here on the diagonal, so you see is exponential minus 4 beta E1. E1 is positive, so this is smaller than 1, and this is hyperbolic tangent, smaller than 1 too. So this quantity here is smaller than 1. So that means that you have that this matrix multiplies by 1 in the direction 1 and multiplies by something smaller than 1 in the direction 2. So, so it's clear that there is a cone that is contracted for this matrix, but also if you switch on theta, you perturb it a little bit. Again, a cone more or less in the direction 1 is certainly uniformly contracted. And therefore, for theta around pi, for theta close to pi, in beta, you have analyticity of the Lyapunov exponent, again by applying Ruel. This is no longer true at theta equal to 0. At theta equal to 0, you see exponential for beta E1 is larger than 1, hyperbolic tangent is smaller than 1. So my this term here, that is in color here in red or whatever, this is something that at least if beta is close to, you can choose a beta such that this term here, by changing the disorder, becomes larger than 1 and smaller than 1. And actually this beta is not difficult to find. It's just, you just compute the expectation of the logarithm, you know, you want to know how much it grows this term here when you multiply these random matrices, when you multiply these random matrices, and then you just have to look at the expectation of the logarithm of this term. This is the thing that I put here. And if the quantity there is equal to 0, that means if the growth of these two components is the same, is around that point that you have this trouble. But actually around, not only for that point that you have this thing that changes becoming larger than 1 and smaller than 1, and so so you really cannot find around that point the contracting cone. And so there is not only one point that gives troubles. There are, in principle, several points because the disorder is spread, delta is positive. But they say the worst case scenario is this one, and this is precisely the way in which McCoy and Wu predict the critical point. This is the expression. So, don't know if it's the first time I was reading it was really not convincing, but okay. But then they are not convinced either, no? And they try to do something deeper. And okay, I go on with the mathematical type of process, and I'm saying, so by the arguments I gave you, is if you are interested in the regularity issue of the expression that was there before, we can just cut this integral to an arbitrary c small as you want, just that is positive, because the trouble is for theta going to 0. So McCoy and Wu choose C equal to delta square. At this stage, why not? And then, since they are convinced that the critical point is beta critical of delta that you saw in the previous page, so they say beta equal beta critical of delta plus something. We would say plus x. They say plus alpha delta square. So they're smarter in a certain sense. And then they don't really look at this quantity. They divide by delta to the 4. But you would agree that if I can prove that this is analytic for alpha, possibly small, but different from 0, and if it is non-analytic for alpha equal to 0, you have solved the problem. Because it's just a change of variables and scales and so on. Okay, here is the criminal step. That was already announced by this thing, is that now McCoy and Wu send delta to 0. And actually, at least if you choose properly the variance of that one, in any case, this expression here, they argue that it converges to this expression where k alpha is a k Bessel function that appears in the next slide. I don't know how much it will speak to you, but and okay, this is the gap. I mean, because we want the result for delta positive, maybe 1 over a billion, but in any case, now for McCoy and Wu, the issue is the regularity of the application from alpha to this expression here, and here you have the k Bessel function if it inspires you, but and the regularity at alpha and the non-regularity at alpha equal to 0 is a really interesting problem. This is a rather explicit but still difficult problem. And in fact, McCoy and Wu solve it with a smart, uncontrolled approximation, because you know, certainly these special functions have developments in all possible sense, and they do a development in both for x and alpha small, and they get to an expression. They choose it widely, so it's quite smart, that step. That is exactly, they get to something that is exactly integrable, and then they finish, because they just look up the solution and they find the result that I stated before. So there is an uncontrolled approximation of that step. So here are, from now, our contributions to these final steps. So under very mild condition on eta, on the disorder, so there's nothing magical about the very specific distribution chosen by McCoy and Wu. This could be confusing reading McCoy and Wu, because you might think that, you know, just that's a very special one because of exact solvability. No, there's nothing. So actually, this limit here is correct. Well, there are probably floating constants, or otherwise one has to choose the variance of the disorder and so on, but this is secondary issues. So this Bessel formula is certainly not a novelty. It's been actually rediscovered at least 10 times in the physical literature. But maybe I don't know. I really claim that there is no proof of this fact, and so now there is one. We brought one. And if I want to give you a proof in a nutshell, you remember theta now is of order delta square by the smart choice of McCoy and Wu, no? They cut the integral there. So that means the term of the diagonal is of order delta square, and then if you develop the term that is on the diagonal, you figure out that is 1. Also the disorder is very, delta is the size of the disorder, and so what you have on the diagonal, you can develop it in delta, and you figure out that is 1 with a deterministic correction of order delta square and a random centered correction of order delta. And then, and therefore, when you do the product of these matrices, you have a dynamics due to this matrix that is very slow, and you can apply approximation a la Struck-Varadhan, for example, with the technical issues of the fact that you are not interested in the convergence of these two-dimensional dynamics only. You are interested in the convergence of the invariant measure and of the convergence of, on top of that, on the convergence of the Lyapunov exponent. So there are some technicalities that I spare to you completely, but this stays in 4 or 5 pages. It's not a matter of, I mean, of course, it's all hidden in theorems that are in the literature, theorems of the 80s. So, okay. And the other contribution that we gave is to prove that this expression here is really real analytic. Actually, we gave the full proof only for alpha in absolute value between 0 and 1. This is because on integer entries, you have different developments. I mean, you can imagine that the Bessel functions behave in a slightly different way. And this proof is relatively heavy. This is not like the previous proof. This is, and so it's already rather long. I have no doubt that it can be pushed, as I say it here, to all alpha different from 0. Because in 0 there is a problem. In 0 it's not analytic. It's only C infinity. And we characterize the singularity in terms of a divergent series, which is essentially the McCoy Wu 1. So the result is that apart from say minimal details, we agree, we have a proof of which we agree with what McCoy Wu claim. And if you want also to give an idea of the proof.
The fact that it's different and not exactly equal is a problem, or?
Wait, different or what?
You said it's not exactly the same.
No, this actually, to be complete, I don't know if the Dussal is there. Actually, in the context of, I mean, they just keep, it's kind of strange. Because if you keep the leading order in the development, you don't get the right result. You have to take also another term. And it's very strange because it looks really smaller, but actually gives this contribution that is there. But this had been already understood by the Dussal in the context of the quantum Ising model. It doesn't change much. It's just a quantitative thing. And you see it in the next slide because also looking at this in my strange. Looks strange in a second, because the point is just an idea of so we were not able to prove the result by doing these developments. We actually took a slightly different way. I don't give you many details, but the idea is the following, also because it resonates with the Young theorem, so it might speak to you. So the point is that k alpha of x is entire, so it's analytic on the whole of C for x positive. Okay. So, but the problem is that in the complex plane it has zeros. So k alpha of x can be 0. And actually k alpha of x is 0 on a countable set that is on the imaginary axis. And as x goes to 0, the zeros fill the imaginary axis. And the crucial point is, of course, the gap that is left here. So it's precisely like in the Young theorem, you have the zeros that pinch down to the and create the singularity there. And okay, an important ingredient is this gap here, and you see that the asymptotics as x goes to 0 of the first 0 of the distance from the origin of the first 0. It goes like pi divided by logarithm of 2 divided by x, so this goes to infinity. Logarithm of 2, and there is a minus gamma. That so that shift that seems to be higher order in reality appears in the final result. So, but I don't know. No, it's qualitatively the result is the same, and in a certain sense also quantitatively, who follows all the constants in a sense. No? But
sorry, and the odd coefficients are 0?
Are 0. Are zeros for this one? Yes. Yeah. Yeah. No, there is an analytic part that we took away from the beginning, and but so yeah, okay, perfect. Yes. Okay, last slide. So of course the question is that are McCoy Wu right? The problem is, as I said before, that one would have to prove that. Sorry for this mistake. It doesn't matter. This is an alpha. Okay. So this to show that this application is analytic for alpha different from 0 and singular C infinity at 0, but you need to prove it for a delta positive extremist mode if you wish, but yeah, I don't know. So this is the only gap, but actually, I don't know, from a mathematical viewpoint, it's of course an enormous gap. I mean, you can build easily counterexamples to it. But of course, there is behind these physical ideas of finite size scaling, and it might be true for reasons that we don't fully understand. Actually, connected to that, I would like to say that, and it's connected to the paper we wrote, because we wrote about this continuum limit of product of random matrices in the physics literature is called often fluid limits. It's actually, I don't understand why in the physics literature is not enough remarks this, but this is really an issue of how universal and robust are these continuum limits. I mean, with the continuum limits you compute and you find the result. I mean, should it be true for delta finite, for the discrete problem, the same result? Actually, this is another set of work, I mean, also with Raphael. For example, in the Derrida lost singularity, if you know this problem, is really remarkable how you pass to this continuum limit and you think you have lost everything, and in reality there is the old structure of the singularity that you have there in the discrete case. Actually, there are other cases in which you lose everything instead. It's rather mysterious for me. But in any case, this result connected to the Derrida lost singularity it goes in the direction of saying that maybe also the McCoy and Wu singularity is true. But I don't know. Then of course, beyond making the McCoy and Wu solution rigorous, there is the fact that Ben Fisher and all the other ones that followed him applied the same ideas to plenty of other systems. And of course, there are plenty of open questions. And I find very strange and a little bit upsetting that all the predictions of Ben Fisher for quantum chains, not only for the quantum Ising chain with disordered transverse field, are unproven. And but the conjectures are very precise. And just for a problem that is very dear to, I said, because in the last 15 years, or maybe almost 15 years, I've been working a lot for the pinning models. Now that we are able to show that in two special cases there is this C-infinity behavior, what about all the other ones? I mean, there is this natural conjecture that when disorder is relevant for pinning, there is this almost complete smoothing. Okay. I'm done. Thank you.
Is there a comment by McCoy?
I would say that no comment from McCoy. I say that maybe I should fear that possibly, but no, I don't know him. I never met him, but I don't know what to say. Knowing him is that he would know that he has understood.
It's Stony Brook, right? I mean,
sorry?
Stony Brook, I said. In Stony Brook, I mean.
Yeah, sure.
Do you have in mind a strategy to attack this delta finite thing, or it's just out of reach?
More than one. It just didn't work up to now. Maybe I don't know. No, but it's yes. I would say that there is even a general. I mean, there are these people proving analyticity. For example, Hans Ruge, proving analyticity of on the line of Ruel that they have generalized to. Actually, I talked to him and to other people in our community. Actually, they have precisely the same problem of these cases in which you may put a small disorder, small randomness, and you go on one side and on the other one, and they agree that in some cases it should stay still analytic, and with Raphael we attempted something based on our earlier work on the Derrida lost singularity. For now it didn't work. I don't know. Maybe Raphael has something to say.
I mean, we have some ideas, but they're still a little half-baked at this point.
So what was it?
we have some ideas, but they're still a little half-baked at this point. So there's some, there are some results about a
Half-baked is not bad.
but
I have the impression it was very raw, but no, it's just the more we had the impression we were very close, and then we went back to her, and then, you know, I don't know.
Okay. There are no other questions. Let's thank you.